was now looking for a distribution that can approximate binomial. And the work of De Moivre is normal approximation to the binomial. So which means when the sample size is large, okay, using binomial distribution, the computation could be cumbersome, could be so difficult. This is a complex, okay, this is complicated, and that is the reason why De Moivre was able to derive a new distribution that we call normal distribution that can actually be used in place of binomial. And that is why his work, his article published in 1733 was called Normal Approximation to the Binomial. Okay, now he was able to prove this. Any question on this? Any question on this? You see the development? You know, statistics, mathematics is like a story. You know, a story that goes on and on. Okay, now it was able to prove that hand combination S, P raised to power S, 1 minus P raised to power this is approximately 1 over square root of 2 pi, okay, P into 1 minus P, N P into 1 minus P, exponential raised to power minus 1 over 2, okay, NP into 1 minus P, X minus N P all squared. Okay, De Moivre was able to prove this to be equal to this. Okay, I'm not going to show you that for now. You can find out, okay, how we go from, this is a binomial distribution. It was able to prove that it's equal to this. I think it used a Stirling. That's somebody called Stirling. It used a Stirling formula. Okay, Stirling actually believed that B equal to 2 pi. Okay, and he also believed that n factorial equal to B n raised to power this exponential raised to power that. So De Moivre actually used the work of Stirling. At the end of the day, he was able to prove that binomial distribution can be approximated using normal. Let me tell you this. If you can actually use a normal to approximate a distribution, you should be celebrating, because a normal distribution is, it has a simplicity in terms of computation. Okay, you're going to see why. Okay, that actually happened. So 1733, that was the work of. So on Friday, you're going to see how we can use a normal distribution to actually compute a binomial problem. Okay, we just need to identify, the condition under which binomial distribution can no longer be used when this, when normal distribution can be used. Then Laplace in 1783 was working on measurement error. And Laplace was actually capitalizing on what Galileo Galilei said in 1632, because Galileo Galilei believed that there's always going to be a distance between two things, maybe module and reality and stuff like that. There's going to be error, and of course, because of the fact that Galileo Galilei said, okay, the error that we're talking about will actually be symmetric. He mentioned the symmetric for the first time. He said it's going to be symmetric about the true value. Laplace now worked on the measurement error and was able to use a normal distribution, okay, as a probability distribution for measurement error. So in statistical analysis, we normally believe errors we have an assumption, error follow normal distribution. If error do not follow normal distribution, then we believe there's a problem. Then we got to use a different model. And of course, Gauss in 1809. In 1809, Gauss worked on the properties of a normal distribution. Okay, Gauss was a mathematician. Gauss actually proved that the mean is this, the variance of S follow normal distribution is sigma squared. of course, you can actually prove, you can prove that how, okay? And if you really want to prove that how, okay, you can try that. Those are the things that we can try, okay? Expected value of x, okay, x, f of s, ds, okay, negative infinity to infinity, okay? We can prove if f of s is normal. We can prove that expected value of s equal to mu. That was done by Gauss. And now, along the line, they changed the name of distribution to Gaussian distribution. When you hear a Gaussian distribution, it also means normal distribution. So what I want to do right now, I actually want to walk you through all the properties of a normal distribution. Okay, I just show you that. Okay, now expected value of s equal to mu. The variance of s equal to sigma squared. But this is what I'm going to do first. Before showing you the derivation of that, okay, I need to first tell you this, that number one, normal distribution or normal density, okay, they actually have their density function to be greater or equal to 0, okay? So what I mean is this, f of s equal 1 over square root of 2 pi sigma square, this x minus mu all squared. Okay, what I mean, f of s greater or equal to 0 for every x lies in real number. Okay, now take a look at this guy. Sigma square is positive. The whole of this guy is going to be positive. Okay, and when you take a look at what we have here, okay, this is positive. Okay, at the end of the day, exponential raised to power minus, what you see there is also going to give a positive. So all of that, so that will show that. So this is going to be number one property of a normal distribution. Okay, number one property of a normal distribution. Okay, f of x greater or equal to 0 for every x in real number. Okay, now number two that I'm going to talk about, all normal curves are symmetric about the mean. All normal curves are symmetric about the mean. Please pay attention. All normal curves are symmetric about the mean. All normal curves are symmetric about the mean. So what do we mean? What do I mean by this? What I mean, f of mu plus s is the same as f of mu minus s. You can try that and see for yourself. This for every x lie in real number. Okay, so what are you going to do? This is f of x, right? When you plug in mu plus x, where you have x, and you plug in mu minus x, they're going to be the same. You can try that. That is what it means that all normal curves are symmetric about the mean. Is there any question here? All what you just need to do, of course, in high school, you do function of function. Plug in this to represent s. When you plug in this to represent x, and you plug in to represent s, the fact that this is squared, they're all going to be the same. Okay, this guy is going to be this guy is going to be the same as that guy. Then number three, okay, all normal curves, okay, have their total area under a curve. They have their total area to be 1. They have their total area. Let me just say they have their total area to be 1. What do I mean? I mean f of s, ds, negative infinity to infinity, has to be equal to 1. How? Okay, if I have integral 1 over square root of 2 pi sigma squared, and I have this guy, ds, how am I